Hello everyone, welcome back. Today's video is on Manning's equation. The learning outcomes of today's video are to define the Manning's equation, and then we're going to evaluate river problems with the Manning's equation. So what is the Manning's equation? It is basically the most general application of our understanding of the conservation of mass to calculate the velocity of a river based off of the friction of the bed, based off of the properties of the soil, the sediment, the plants growing through it, the slope of the river, and the cross-sectional area through which the creek is flowing. It is really old. It was discovered in the late 1800s, but some background on how it was discovered in the early 1800s. There was a lot of work looking at the flow through water through pipes because they were setting up lots of drinking water infrastructure. People were very interested in the flow of water through man-made pipe systems. And so the Darcy-Weisbach equation is what you use if you want to know the loss of pressure as you flow water through a pipe. And so Manning found that a river is basically an open face pipe. And so by modifying this equation, we're able to measure the velocity, measure the loss of inertia of this water as it's flowing over this complex, highly full of friction surface, which is our creek bed. The sediment and the pebbles are all going to hold on to that water and inhibit it from flowing as quickly. If you have a lot of big boulders in a stream, it's not going to flow as quickly. And so Manning actually takes that into account in his equation, and we're able to model a stream pretty well and calculate the normal depth of a stream. And that's the depth of the stream without any other obstructions causing water to back up. So if there's a dam right down the stream from you, that's going to sort of render the Manning's equation not relevant because of this dam is backing up water to your point of reference. And then different weirs and things above can also cause the flow that you're experiencing to not be Manning's equation calculable. So the Manning's equation allows you to calculate the flow of the river under normal conditions. And so this is the equation in question. There are two versions, one for US units and one for SI units. And you'll notice the only difference between the two of them is that the US units has a 1.49 to adjust for that change in unit base, and then SI is just 1. And so just know that there's a difference between these two. There's a difference based off of what unit you are working in. And so here we have Q equals VA equals 1 over, or 1.49 over N times A times R2 to the 2/3 power times S to the 1/2 power, or the square root of S. So you'll see S to the 1/2, or you'll see the square root of S. They mean the same thing. N is our Manning's coefficient. This is determined experimentally, and this is sort of our empirical value that allows us to sort of fudge the numbers a little bit. A is our cross-sectional area. R is our hydraulic radius, which we'll discuss a little later. S is the slope of the river, and then Q is our volume per second. So in the US one, it is feet cubed, or cubic feet per second, and the SI is cubic meters per second. So Manning's coefficient represents the roughness of our channel. So you'll see here we have a table of various Manning roughness coefficients. Concrete, made with steel forms has a roughness coefficient of 0.011. Concrete made with wooden forms is a bit rougher, so it has a Manning's roughness coefficient of 0.015. Corrugated metal is rougher than concrete, and that's because of our corrugation. You have those ridges that's inhibiting flow a bit more. Plastic is very smooth, and so it has a very small Manning's roughness coefficient. So as we increase the Manning's roughness coefficient, our flows are going to decrease, and we're increasing the roughness of the surface as this number increases. And this is sort of our fudge factor. As you get into more complex environmental flows equations, you'll get more fudge factors that allow you to sort of manipulate the equation a little bit to best suit the situation at hand. The hydraulic radius is the cross-sectional area of our river divided by the perimeter. It's sort of like the radius of a circle. And as we've learned, the riverbed is pushing the river around because of friction. And so the friction of the bed is determined by the material that bed is made out of, which is what the Manning's coefficient represents. And the hydraulic radius tells you how much of that riverbed is, how much of the water is in contact with that riverbed. Is it a really wide, shallow river? That's going to have a really large or a really low hydraulic radius because the perimeter is so large. Or is it more of a concentrated channel? That's going to have a larger hydraulic radius, and it's going to flow faster. For this course, and in most of my courses, we'll typically assume that this is a rectangular channel. So that means the area of our channel is the base times the height. The base times the height. Let me get my pen out. Okay. So we have our rectangular channel, we have the height, and then we have the base. And so area is base times height. And so that's our area. And then our perimeter is two heights. So there's one on one side and one on the other side. So 2 times 2 heights plus our base length. So 2h plus b. And you divide those by each other. So area divided by perimeter, BH divided by 2H plus B gets you your hydraulic radius. Okay. Let's see. Let me get out of that. Okay. Our next variable is river slope. Slope is a unitless measurement. You may have seen this if you're driving in the mountains ever. They might tell you the slope or the grade of the road you're driving down, and that's typically represented as a percent, which is unitless. A 4% grade is a 0.04 slope. It is a unitless value. It's a distance over a distance. And so it's the change in elevation of our stream over our river's length. And so I might just provide the elevation of our headwaters and have you divide that by the length of the river instead of just providing the river slope on its own. And so that covers all of the variables of the Manning's equation. So now let's move on to an example. So consider an open channel of rectangular cross-section with a bottom width of 4 feet, a depth of 2 feet. The bottom slope of the channel is 0.004 and it's made of concrete. What would the average flow velocity of the water be, and what is the volumetric flow rate? So I know from my table over here that the Manning's coefficient of concrete is 0.011. 0.011. Let's get out my tool again. Equals 0.011. Our area of our rectangular river is our base times our height. And so in this case, that's 2 times 4. And so our area is 8 square feet. Our perimeter is the same as the last 2 slides ago. It's 2 times our depth plus our base width. And so in this case, that's 2 times 2 plus 4, which is 8. Our perimeter is 8 feet. And so our hydraulic radius is 8 divided by 8. 8 square feet divided by 8 feet gives us 1 foot hydraulic radius. 1 foot hydraulic radius. We are provided the slope. And so now we can actually enter this into our equation. And you'll note on the first slide, we had flow rate equals velocity times area equals our whole equation, 1.49. Since we're in feet, we're in the US system, so we're going to use 1.49. Then we have area times R to the 2/3, hydraulic radius to the 2/3 power, and slope to the 1/2 power. And you'll notice if I cross out area here in both these equations, I really am just working with the stream's velocity. Flow rate equals velocity times area. And so the Manning's equation is really just dealing with the velocity of the river ultimately. That's what's being impacted by our roughness coefficient, by our hydraulic radius, and our slope. And so this question wants me to have both. So if I input 0.011 in over here and a hydraulic radius of 1 and my slope of 0.0004, raise those to the 2/3 and 1/2 power, I get a velocity of 2.7 feet per second. 2.7 feet per second. And my flow rate is equivalent to velocity times area. My area is 8 in this case. And so my flow rate is about 16, a little larger than 16. So like 20-ish. 20-ish. And so that concludes this presentation. I want you to think about what these variables are doing ultimately to the flow of our channel. If I increase the slope of my river, my velocity is going to increase. If I increase the hydraulic radius, if I increase the area, that is going to increase the velocity of my river. So I really want you to think about these variables and ultimately what they're doing to the stream flow. And that concludes the video. Thank you and take care.